Hello, in this presentation I'm going to talk about the use of Lagrangian coherent structures to study the organization of fountains in stratified media. Why is it important to study turbulent fountains in stratified media? Turbulent fountains arise in various environments, from large magma chambers in the Earth's crust to oceans and in the atmosphere. It is also present in technological applications. In this work, we focus on an Uruguayan technological device to mitigate damage caused in crops by radiation frost. Radiation frost occurs in temperate regions on clear and still nights. At approximately 100 meters above the surface, temperature at sunset remains constant during the whole night. In the absence of clouds, Earth's surface cools by radiation through the atmosphere. This leads to a stratification of the air with a linear profile in temperature. As a consequence, temperatures below a sharpened limit result in severe crop damage. The selective inverted sink, or SIS, is used to reduce damage caused by radiation frost. This device expels the cold air from the surface into a vertical jet. The jet captures warmer fluid from higher air strata as it runs through it, increasing the jet's temperature. The fountain is formed after the jet reaches a maximum height, then reverses its direction and falls until buoyancy force becomes null. This height is where spreading occurs and is called spreading height. In order to contribute to the SIS design, we performed experiments and numerical simulations. In the laboratory, a heavy fluid jet of cold water was injected vertically upwards into a linearly stratified atmosphere, from 15 degrees Celsius to 30 degrees Celsius. We considered three configurations shown in the table, combining jet temperature of 15 and 18 degrees Celsius and jet velocity fluctuations of 2 and 20%. These configurations were named Grid 15, Free 15, and Free 18. We performed numerical simulations validated with experiments with the open-source package CAFA3D. It is a fully implicit three-dimensional incompressible implementation of finite volume method, with second-order accuracy in space and time. The solver uses curvilinear meshes structured by blocks aimed at Navier-Stokes equations in complex geometry. We validated the Free 15 and Grid 15 numerical calculations with experimental results. Finite-time Lyapunov exponents, or FTLE fields, measure the maximum exponential separation between initially closed trajectories during a finite-time interval tau. Ridges of FTL fields act as flow material barriers. These structures, also known as Lagrangian coherent structures, or LCS, organize the flow since it separates regions with different flow dynamics. FTLE, computed forward in time, generates repulsive barriers, while FTLE, computed backward in time, generates attractive barriers. Our results show 5 predominant LCS that organize the flow. The first LCS consists of a material barrier at the top of the fountain, making the flow reverse its direction. The falling flow can be attracted to the second or the third LCS. The second LCS is located along the fountain axis and from the ground to the maximum height. This structure is responsible of 1. The entrainment of fluid from the surroundings, and 2. The entrainment of fluid into the upward jet, which is mostly re-entrainment. The third LCS is located around the spreading height and leads the flow radially away from the fountain axis. The fourth LCS prevents the spreading flow to fall beyond the spreading height. And the fifth LCS limits the edge of the jet and is sometimes connected to the fourth LCS. The figure on the left shows representative particle trajectories among the different LCS. LCS detection enables an accurate localization of the jet boundary. Therefore, we calculate the cumulative normalized flow rate at this boundary for the three configurations, shown in the figure on the right. Comparing the three configurations, Grid 15 has a higher entrainment for lower heights. This could be explained since the turbulence of the jet provides a better mixing with its surroundings. Therefore, the upward cold flow increases faster its temperature for lower height, which also explains a lower spreading height. Finally, we sum up our results stating that for the three configurations, the flow is organized through a set of LCS. The LCS determines boundaries of fountains and characteristic heights, and the entrainment and self-entrainment can be computed through the boundaries determined by LCS. Thank you.